All right. So for Unit 3, circular motion and gravitation, right? Key concepts for this unit. Okay, we started out with uniform circular motion. Okay, and here's what we need to know about uniform circular motion. Okay, how it happens. Slash the principles of it. Okay, so what I mean by the principles of it is this. Anything undergoing uniform circular motion is undergoing uniformly accelerated motion because there is a centripetal force that is pulling the object back towards the center of the circle. Okay, I don't have my speaker on. Not in case anybody in the live stream wants to talk. Here's another one. Okay, now you guys are on in case anyone tried to say anything. Okay, so how it happens, okay, the principles of it. So yeah, like I said, it's uniform accelerated motion. There's a force that's acting towards the center, okay? That's what causes it to constantly change velocity. However, it is traveling at a constant speed. Even though it is accelerating, it is traveling at a constant speed. The magnitude doesn't change. Only the direction changes for an object undergoing uniform circular motion. Okay? Now, our examples of uniform circular motion that we talked about most were unbanked and banked curves. Right? Could you expect a problem on your final exam about either of those? Yeah. Either, maybe both. Okay, but certainly either. One or the other is certainly the other. Okay. So remember, what keeps you in an unbanked curve? Friction, right? So our centripetal force is provided by the force of friction, whereas with bank curves, it's provided by the the horizontal component of the normal force of the corner, okay? And we have this whole other formula for that, tan of theta equals v squared over r times g. Okay. So that covers basically all the stuff, including artificial gravity. That was also uniform circular motion. Okay, and in that case, we want the centripetal force to equal the force of gravity for the spinning cylinder or drum, okay, that's providing the artificial gravity. Okay, then we went into vertical or non-uniform circular motion. Okay, and we talked about 3 different points in a vertical circle. We talked about this point in a vertical circle, this point in a vertical circle, and this point in a vertical circle. Okay. What do we need to remember about all 3 of those? Applies to all vertical circular motion. FC equals, nope. Nope. Forces in minus forces out. In some cases, it could be equal to Fg, okay? But we don't know for sure because it's situational, okay? Okay, this always applies. This is what makes it situational. Okay, forces in minus forces out. So for this cart, gravity is acting out. Normal force is acting in. In that situation, you would feel what? Heavy or light? Heavy. That is where you feel the heaviest, because gravity's trying to pull you out. The track has to push harder because it's not just gravity, it's also your inertia. All of that makes you want to leave the circle. You feel heaviest at the bottom of a vertical circle. Okay? In this case, when you're going under the top of the vertical circle, gravity is pulling you in. And if you're just going fast enough to stay in the circle, that's all it's pulling you in. You're at your minimum speed in that situation. If you're going faster than the minimum speed, then you push on the track and the track pushes back, and you'd have normal force also acting in, and there are no forces acting out in that situation. Okay, and we watched the Cirque du Soleil video, and we could kind of see when all of these things were happening, right? The difference is when they were on the top of the circle, when they're inside the circle. If they were going fast enough, they just stuck to the inside. They literally didn't fall. Okay, so that was that situation there. Now, going over the top of a vertical circle is the situation where you can produce a feeling of weightlessness, apparent weightlessness, okay, but weightlessness nonetheless. Okay, in this situation, gravity is pulling in, so you're never actually weightless. Okay, you still have weight, but if you go fast enough, you lose contact with the track. Okay, and in that situation, normal force would then be 0, and that's when you would feel apparently weightless. Okay, and we watched the video of those guys on the plane. Okay, the music video of them, those guys on the plane doing that. Okay. All right. Should you expect a vertical circular motion question on your final exam? If you weren't expecting it, expect it now. There's one. It's a roller coaster going over the vertical circle. True story. Okay, so make sure you know how to solve a vertical circular motion problem, and there's a couple of multiple choice dealing with how you feel at each one of these points, which we just talked about. Okay, so that's kind of checking your understanding of vertical circular motion. All right, that was like the first half of the unit, those two types of circles. Okay, then we talked about universal gravitation. Because understanding how gravity worked would lead us to satellite motion and gravitational fields and the rest of the unit. Okay, so universal gravitation talked about how the force of gravity is related to the universal gravitational constant, the two masses that are interacting, and the square of their separation distance. Now, while there's very little problem solving, like just to do with universal gravitation, it is obviously part of satellite motion. Spoiler alert, there's a satellite question on your final. Okay, but there's not really any calculating just to do with this formula by itself. That said, there are a number of multiple choice questions that ask about your understanding of it. Okay, those kind of questions could focus on things like, what's the effect of increasing the separation distance? Okay, so if I make R twice as big, I double R. I take the two objects and I make them twice as far apart. What happens to the force of gravity? Up or down? Down. How much? I double the distance. How much does force of gravity go down? 4 times. Remember, R is squared. So if I double the distance, it's actually dividing by 4 times as large of a number, okay, because it's an exponential relationship. R is squared. Okay, so the further apart things get, they are exponentially less attracted to each other gravitationally. Okay. What if I double one of the masses? What will happen to FG? It'll become 2 times bigger. Okay, there's no squares up here, right? If I double just one of the masses, I suddenly have twice as much mass. Boom. Okay, now I get twice as much gravity. Okay, everybody with me on that? All right, so that's all you need to know about universal gravitation. Obviously, being able to manipulate that formula in the context of this is important. Okay, in order for something to orbit something else, the centripetal force is going to be provided by this force of gravity. Okay, so that was one of the situations with satellite motion. The other situation would be if, instead of giving you the ability to get V, I give you what instead? Yeah, Kai's giving me the symbol over there, T. I give you period instead. I tell you how long it takes to make one orbit. Okay, remember that in this situation was where we had to sometimes substitute in for V. We had to say that V is 2 pi r over T. Right? Then you would have to just substitute this in for V squared, which means you square the whole thing and plug it in there. So you would have m 4 pi squared r squared over T squared times r. This r and that will cancel, and then I'm back to this, g times m1 times m2 over r squared. Is that ringing a bell? I got masses on both sides. What happens to one of them? One of them cancels. Which one cancels? The orbiting mass or the central mass? The orbiting mass. Okay? The orbiting mass cancels because all things fall at the same rate. All things are equally gravitationally affected at a given distance because of, what number are we on? 5? Because of gravitational field strength. Okay, that is little g, okay, or acceleration due to gravity, is big G times mass over r squared. And in this case, that mass is the central mass. Okay, remember that we derive this formula by doing this. Fg equals Fg. That's m times g equals big G times m1 times m2 over r squared. The mass that cancels is the smaller mass. Okay? The one generating the field, the larger one, is the one that stays in the formula. And that's because all things fall at the same rate. At the Earth's surface, all things fall at 9.81. Okay? As distance increases, the acceleration due to gravity changes. But it's still the same for all objects at those distances. Right? Does that make sense to everybody? Right, and that was the end of that unit. There really wasn't much in that unit. It was pretty short. I think we were done that in like 3 weeks. Okay, but we ended it during the lockdown, so you guys did that test virtually. Okay, we did the Google form of that test. So speaking of tests, I did make a spreadsheet last night to figure out which was everybody's worst test. Okay, so I now have it marked on my spreadsheet. This is your worst unit exam. Remember that if you do better on your final, I will replace your lowest unit exam mark with your final exam mark, okay, as well. And of course, if you do better on your final exam than you did in the course, then I'll count your final exam. If you don't, then I don't count it. Okay, everybody with me? Unless I'm counting it for your worst final. So it could still count. It could count twice, it could count never, it could count once, okay? Depends entirely on how you do on it and how you've been doing thus far. Okay, but there was a real trend towards this was the worst unit exam because it was the Google form. Okay, which is why I made it worth less than all the other ones. If you recall, I did that during that unit as well. Okay, all right, so that's the stuff that's in that unit. Let's talk about your final exam because I told you I'd give you some details about that today. So you'll probably want to write a few of these things down. Okay. So, in your multiple choice, sorry, there are 21 multiple choice. And there are 12 written. Okay, so the format of the final is exactly the same as your unit exams. There's some multiple choice and then there's some problem solving, okay? All that's different is it's a little bit longer. Okay, you've had some unit exams where there were like 8 or 9 written, there's 12 on your final. Okay, most of your unit exams have been around 20 multiple choice, there's 21 here. Okay, I don't think that it's gonna be any problem for you to finish this in 2 hours, right? I had the key done in 35 minutes. Okay, so that's definitely erring on the side of really fair toward you guys, okay, because it was quick. Right? All right, so multiple choice questions. Okay, V equals D over T. And in regards to V equals D over T, it's the whole like in combination with vectors and scalars, like, you know, speed versus velocity. So there's some calculating, simple calculating, but having to remember, all right, I'm solving for velocity, I do it this way. I'm solving for speed, I do it this way. Okay, so there's a couple of questions about that. Okay, there's a very simple vector question. There's 2 questions about Newton's laws, multiple choice questions about Newton's laws. There's 2 very simple Newton's second law multiple choice questions. And by that I mean like one of them involves like one calculation, like you're either dividing 2 numbers or multiplying 2 numbers or adding 2 numbers, like super simple, okay? And the other one doesn't even need a calculation.
On the topic, so the first 2 Newton's laws questions are like just broad Newton's laws, and then there's
Yes.
2 specifically for Newton's second law?
Yes, the first 2 are like, here's a situation, which of Newton's laws applies to it, kind of question. Okay, 2 more Newton's second law questions, just again, the real world application kind of things. What if this happens, what happens to acceleration, or if this happens, what happens to force? Those kind of situational type questions. Okay, then we got a question about uniform circular motion. And one about gravitational field strength. Then we got a couple of simple harmonic motion questions. Again, just the principles of simple harmonic motion. Then 3 questions about wave behavior. Then a question about Kepler's laws. And the last 4 questions are on wave behavior. So Unit 4 gets the most multiple choice questions because it lends itself better to that than the other units do. Ready for the written? Question number 1. Projectile motion. Question number 2, graphing. Okay, so you'd be asked to interpret and do some calculations to do with either a position or velocity versus time graph. Question 3, gravitational field strength. Okay, question number 4, Newton's second law. Problem. Question 5, conservation of mechanical energy. Six is vertical circular motion. Seven, satellite question. Eight, Doppler question. Nine, standing waves, air column question. Ten is a uniform circular motion question. The 11 is a wave behavior and interference question. The 12 is a Newton's second law problem. That's it. Okay. Having given you extraordinary detail of your final exam. Why? No, I was asking that of you, not me. I know the answer. Because I want you to focus your studying on the skills that need to be demonstrated. Okay? We took 2 extra days for classes because of the lockdown. So we changed our exam schedule. There were supposed to be 2 more days for exam writing. Okay, but people were feeling kind of pressed for time, and so we took 2 extra days for classes, which means your exam schedule is more condensed now, right? So you have less time to prepare. So what I'm doing is helping you to focus your preparation. You know now exactly what to study for physics. Study that would be my advice. It's very simple advice, but I'm a simple man. Okay, study that stuff. Practice problems like I've told you are going to be on the test. Okay, focus your studying to do your best on that material. Okay, obviously you guys, according to the exam schedule, are writing in Miss Paulgard's room, okay, St. Joan of Arc. So next room down on the right-hand side, okay, is where you guys will be writing. Okay, and Ms. Sakura will be supervising you. Right? I will pop in periodically, okay, throughout the test to check on you and see how you're doing. Right? Right, now we have talked about what kinds of things you want to bring to the test. Okay, make sure you bring those pencils, pens. Okay, your calculator, I will have instructions on the desk for how to clear your calculator. Okay, Please follow those instructions and then leave the calculator's memory cleared screen on so that when I walk by I can see that your calculator is clear. Okay? Make sure you follow the instructions to the letter because it ends up that people don't. I end up resetting half of them myself because they only clear the RAM and not the memory. Okay, so make sure you follow the instructions to the letter so that you clear the right memory. Okay? Make sure you got fresh batteries in that calculator. I think we talked about that. Something to drink, a little snack, not Doritos, okay? Or carrots, or oranges.
Or chicken.
Or what?
Chicken.
Or yeah, or a whole cooked chicken from Sophie's. Okay. You will get a fresh formula sheet. Okay, so don't bring yours. And I don't know how much stuff you've written on yours. So you're getting a fresh formula sheet for the final. So all you need to bring is what you're going to write with. There will be in each room, I think, a bin for phones and stuff. Okay, so just make sure that you put those, turn them off and put them where they're supposed to be, including any watches that may communicate with them. Okay, will also need to be surrendered and put in there so that they can't be used to communicate during the test. That's it. Okay, questions from you guys? Anything you want me to go over? Demonstrate.
So I don't remember if we went over the unit test for waves. I believe we did.
Yes, we
but,
did.
As some feedback for that, what do you suggest we work on to improve that?
Well, the questions on your final that have to do with waves, you've got a Doppler question, right? You got an interference question. You got a wave. You got some wave behavior questions in the multiple choice. Okay, you got an air column question here. So my suggestion would be do those. Okay, practice a bunch of those kind of questions. Yeah. Okay, what else, guys?
Hey, could you do number 9 from the review package?
Okay. Look it up here. Okay, yeah, I think actually we did one like this yesterday. It's certainly worth doing again. Okay. So for number 9, we have a 3.5 kilogram mass sitting on a level surface. Okay, connected over a pulley. Okay, to a hanging 2.5 kilogram mass. Okay, coefficient of friction on the level surface is 0.245. Okay, we're looking for the acceleration of the 2.5 kilogram mass. Okay, so identifying forces is our first thing here. We got a force of gravity here. Okay, pulling down on the 2.5 kilogram mass. At 24.525 for that one. Okay, and it tells us there's a coefficient of friction here, so obviously we have a force of friction acting on the 3.5 kilogram box. How do I calculate that? Right? Mu times normal force will get me the force of friction. Okay, because this is a level surface, normal force is equal to force of gravity. Okay, the only time they're not equal is if it's pulled up or down, okay, at an angle. Okay, so I will just calculate the force of gravity here. Oop, not minus, times 9.81. All right, so there's my force of gravity. I multiply that by mu, 0.245. There's my force of friction, 8.41 newtons. Okay, now I have all the forces that matter in the system identified. Okay, force of gravity and normal force no longer play any part. Why? What do they do to each other? They cancel. Remember, we're trying to find the net force here, and the net force is the vector sum of all forces, and those two forces add up to 0, so the vector sum is not important. Okay? So now, here's what I'm left with. Is this a system? It is. It's two masses connected that are going to accelerate together, right, at the same rate. That's the key. Their acceleration will be the same. So in actual fact, what I have here is a system with a mass of 6 kilograms being pulled one direction by 24.525 newtons and resisted in the other direction by 8.41 newtons. Can I calculate my net force? Okay, I mean, that's the purpose of a free body diagram, is to help me calculate my net force. Net force is the vector sum of all forces, so that'll be 24.525 minus 8.41. So we have a net force of 16.11 newtons. Okay, and I want to find the acceleration of the 2.5 kilogram mass. So I take my net force, 16.11 newtons, and I divide by what? 6. Okay, not by 2.5. The whole system accelerates. Therefore, I divide by the mass of the system. And that's the trick with systems, is you always have to remember you're using the whole mass and that the forces act on the whole system when we're getting to this point. Okay, and so when we do that, we should get our 2.7 meters per second squared, and we can give a direction because it did ask about just this mass. That's down. Okay, had they said what's the acceleration of the system, then I would have to stop at 2.7 meters per second squared because the parts of the system accelerate in different directions. Okay. All right, what else, guys? Okay, cool. Projectile motion, okay. Okay, I'll give you guys a little bit of time to try that one on your own before I do it. What?
65 or 6.5?
That is 65. Okay, so this object is going to follow a projectile arc that will re-encounter the ground that is the same height over there. Okay, we want to break this up into our vertical components and horizontal components. Okay, so the vertical part, or vertical component, is going to be our initial vertical velocity, and this horizontal part, okay, will be our constant horizontal speed. Okay, all right, so I've got to calculate those things. Right, so I'm going to calculate VI. It's the opposite side, so it'll be the sine of 40 times 65. Okay, so 41.78. okay, meters per second, and that's positive. What's VF if we're talking about the whole trip? Negative 41.78. Okay, so we got that. And the other thing we know vertically, acceleration, negative 9.81 meters per second squared. All right, so that's the vertical information we have. We also said we needed to calculate the horizontal speed. Okay, so that will be the cos of 40 times 65. All right, so 49.79. Meters per second. Okay, what can I calculate with my vertical information right now? Time, right, okay, and that's what we always do, right? We're always looking for the time here, okay? Because the time applies to both the vertical and the horizontal parts. So VF minus VI over A will get me time, so that'll be negative 41.78 minus 41.78 divided by negative 9.81. Okay, so in my calculator, I'm going to shortcut that just a little bit. I'm going to take that number, multiply it by 2, because that's what negative minus the positive equals, okay? And then I'm going to divide that by 9.81. Okay, so I've got 8.5 seconds. I'll keep all those decimals for later, okay? 8.51 seconds. So I'm going to bring that over here, okay? Time equals 8.51 seconds. D equals V times T. Now I have both of those, so I can calculate the horizontal distance. So that'll be 49.79 with all the decimals, multiplied by the time, 8.51 with all the decimals, okay, for the purposes of significant figures. Okay, so I'm going to take that answer and multiply it by that. That was my horizontal speed. Okay, it's going to travel 4.2 times 10 to the 2 meters. Okay, everybody all right with that? Okay. What changes if I'm looking for the maximum height? Maximum height occurs right here. Right? VF becomes what? 0. Right. The vertical speed or vertical velocity at that point is 0 because that's where it's turning around and starting to fall back down. Okay. This will find us our maximum height, which is our vertical displacement. So I know VF, I know A, and I know VI. That doesn't change. Okay. And I'm looking for D. So I would say VF squared equals VI squared, because I have both of those, plus 2A, I have that, D, which I'm looking for. Right? So D will equal VF squared minus VI squared over 2A. So that'll be 0 squared minus 41.78 squared divided by 19.62. Okay? And that's negative. All right, so 0 minus 41. Oh, sorry, we got to use the actual number here. That number squared, okay, divided by negative 19.62. Okay, so the maximum height will be 89 meters. Okay, what else, guys? Bank curve, okay. You may.
Thanks.
Okay, there you go. Give that one a try. I'll give you a few minutes on that one. Okay, so we got a bank curve here. We know that theta is 6.0 degrees. We know the radius is 215 meters. We're looking for the speed at which it can be taken. Okay? We know that for bank curves, the tan of theta equals v squared over r times g. Okay, so we're manipulating for v. So I'm going to multiply both sides by r times g, and then I'm going to square root to get v. So v will equal the square root of 215 times 9.81 times the tan of 6. So, square root of 215 times 9.81 times the tan of 6. All right, so it can be taken at 15 meters per second. Okay, what else? Yes, you guys asked some good questions here the last couple of days. I used all of your questions from yesterday with my period 4. They were quite impressed, actually. Okay, I'll give you a little bit more time there, guys, to work on the review package, and hopefully some more questions will come up.
Do you know what the principles involved when discussing vertical and non-circular motion?
Okay, so the principles of non-uniform or vertical circular motion are that the speed of the object changes as it moves through the circle, because the force is acting on it change as it moves through the circle, which is the exact opposite of uniform circular motion, where the force is constant and the speed is constant and the acceleration is constant and all of that stuff. Okay, so since the forces are changing, because gravity is involved, okay, then the speed changes. That's really all the principles are. Okay? There still has to be a force there pulling towards the middle, but it changes, so the speed changes as a result. Where does it go fastest? Around the vertical circle. Where do you suppose it goes fastest, top or bottom? Bottom, right? That's where gravity is accelerating. So bottom's fastest. That's why we feel heaviest there. Okay, that's why it takes the most tension to hold something in that circle. Okay, all of that kind of stuff. Top. Okay, if we go just fast enough, there's no tension in the string at all. Okay, so it goes over the top. Okay, what else? Okay, well, keep working on the review. Something else will probably come up. Go over that. Okay, so vertical circular motion problem. Okay, we're going over the top of the vertical circle. So Fn is acting out, Fg is acting in. We're being asked to find the apparent weight. That's Fn. Okay, so there's one of those things, background knowledge, right? I need to remember that apparent weight is normal force, or this is a pretty tough question. Okay, so what we're told here is we're told the radius. Okay, 250 meters. We're told the mass, 1,500 kilograms. We're told the speed, 13 meters per second. And we know that because it's a vertical circle, we're looking at forces in, gravity, minus forces out, normal force. Okay, I want to solve for normal force. So right now, I'm going to add normal force to the other side so that it's positive. And then I'm going to subtract Fc back over to the other side. Okay, that's going to get me my normal force. Everybody okay with that? Okay, so now I can plug in my actual formula. So normal force will be m times g minus mv squared over r. Okay, so that's going to be 1,500 times 9.81 minus 1,500 times 13 squared divided by 250. Hopefully I picked numbers and I didn't get a negative number here. Okay. All right, so 1,500 times 9.81 minus 1,500 times 13 squared divided by 250. Okay, so the apparent weight of the car is 13,701 newtons. Okay, or 1.3. Actually, we only have two significant figures there. 1.4 times 10 to the 4 newtons. Okay, everybody all right with that? Okay, what else do you want to go over?
Can you use satellite motion?
Okay, satellite question. It's, okay, try that one. Okay, so for this one here, first thing we need to do is get the actual radius, because that is the distance above the surface, and I need the distance from center to center. Okay, so I'm going to take my 1.5 times 10 to the 7 and add it to 6.37 times 10 to the 6 to get my actual overall radius. Okay, so 6.37 E6 and plus 1.5, whoop, 7, okay. All right, so we got 2.137 times 10 to the 7. Meters is our actual radius, okay? It's a satellite. FC equals FG. So that means mv squared over r equals big G times mass 1 times mass 2 over r squared. Did I need to give you the mass of the satellite? No. Okay, so mass of the satellite is canceled. I'm looking for how fast it's moving, right? Yeah, okay, so looking for v. So I'm going to multiply both sides by r. When I do that, the squared is going to cancel, and then I'm going to square root to get v. Okay, so when I plug in my numbers here, all right, v is going to be 6.67 times 10 to the minus 11, big G, times the mass of the Earth, 5.98 times 10 to the 24 kilograms, divided by our 2.137 times 10 to the 7, and then square root all of that, and we'll get v. Okay, so we'll have our 6.67 negative 11 times 5.98 E24 divided by 2.137 7, and then we square root that. So it's got to move at 4.3 times, actually we have two significant figures. So 4.3 times 10 to the 3 meters per second. Alright, so that would be a typical satellite motion question. Okay, what else? Okay. I had a bank curve question here. Yeah, okay, here's a bank curve question. You guys can give that one a try. All right, so for an unbanked curve, okay, looking for the radius of an unbanked curve with a coefficient of friction of 0.475 that can be taken at 20 meters per second by a 2,000 kilogram car. Okay, give you a few minutes on that one. All right, so on this one, we're looking for the radius of this curve. So we're looking for r. Okay, we know that v is 20 meters per second. We know that the coefficient of friction is 0.475, and we know the mass of the car, but it won't matter. Okay, so centripetal force is provided by the force of friction in an unbanked curve. Okay, that means mv squared over r, okay, equals mu times the normal force. Since it's not banked, normal force is equal to gravity. Okay, that's why m cancels. Okay, that's why m is not important in this question. All right, I'm trying to find r, so I'm going to bring r over to this side here and divide both sides by mu times g. Okay, and what I'll be left with is that r equals v squared over mu times g. Okay, and so that'll be 20 squared divided by 0.475 times 9.81. Okay, so it's got a radius of 86 meters. All right. Good with that one? Okay, got any other requests? Gravitational field strength question. Okay, give that one a try. All right, so looking for mass of the planet here, we know that G equals big G times the mass of the planet over r squared. Okay, so we have r, we have little g, and obviously we have big G. So we're going to multiply both sides by r squared and then divide both sides by big G. That'll give us m. So we'll have 7.35 times 10 to the 7 squared times 9.45 divided by 6.67 times 10 to the minus 11. Okay, and that's going to give us a nice big number. Okay, so 7.35 e 7 squared times 9.45, okay, divided by 6.67. Okay, so we're looking at something a little bit heavier than Earth, 7.7. So we have three significant figures, don't we? 7.65 times 10 to the 26 kilograms. Okay, everybody good with that? All right, thanks for a good semester. And thanks to you guys who couldn't be here today. I'm sorry about that. As soon as I know what's going on with your exams, that's especially for you guys who are on the live stream, I will put it in the stream. I would imagine there's got to be an email going out to people because that's going to be some pretty important news, but I don't know because it's above my pay grade. Okay? So hopefully we'll know soon.